All right, so we've talked quite a bit about significance testing. We know that a significance test is used to test some sort of hypotheses. So you would have a null hypothesis, an alternative hypothesis. You would go out and collect some data, and from that data, you would calculate the probability. So far, we have studied how to calculate those probabilities using a t statistic. Right? And you would look at that probability and say, if the null hypothesis is true, what is the probability of getting the results that we got in this particular sample? You calculate that probability, and if p is low, reject the hoe. If your p-value is greater than 0.05, then you would fail to reject the null hypothesis. But at the end of the day, what if you get it wrong? There are errors that can happen whenever you're conducting a significance test, just like there's errors that can happen in the courtroom. Remember, in the criminal justice system, we say innocent until proven guilty. So our null hypothesis is that the defendant is innocent, and our alternative hypothesis is that the defendant is guilty. And you're going to assume that they are innocent until they can prove that the person is guilty. Now, on the day of the trial, the actual truth is out there. We don't know what it is, but it's out there, right? So either the person really is innocent or the person really is guilty. So either the null hypothesis is actually true or the alternative hypothesis is actually true. But we don't know what the real truth is. That's why we're having the trial, so the jury can weigh the evidence of this stuff. And so the jury comes back and they'll either say guilty or not guilty. In the case of guilty, they're rejecting the null hypothesis because they have enough proof to show that they're guilty. For the decision not guilty, that just means that they don't have enough proof to say that the defendant is guilty. Now, in two of these circumstances, we've made the right decision. If the person really is guilty and the jury says they're guilty, that's the correct decision. If the person is really truly innocent and the jury decides that they're not guilty, that's also the right decision. But in two outcomes, we end up with the wrong decision. If a person is really truly innocent, but the jury finds them guilty, that's what we call a type 1 error. Right? Type 1 error is when you reject the null hypothesis, but you shouldn't have because the null hypothesis was actually true. So type 1 error is where the innocent person goes to jail. Type 2 error is the opposite of that. Type 2 error is when a guilty person is set free. So if the person is really truly guilty, but the jury finds them not guilty, that is a type 2 error, when you fail to reject the null hypothesis, but the alternative hypothesis was actually true. So now for more formal definitions of type 1 and type 2 error. The probability that we reject the null hypothesis when the null hypothesis was actually true, that's a type 1 error. Reject the null hypothesis when you shouldn't have. Now notice that it says probability. When you set your significance level, you're setting a probability to reject the null hypothesis. The probability of you getting it wrong is your alpha. So if your alpha is 0.05, that means there's a 5% chance that you make a type 1 error. So if a type 1 error is really, really bad, then you might want to choose a lower significance level so that you're less likely to make this type of mistake. Now, the probability that we do not reject the null hypothesis when the alternative hypothesis was actually true, that's a type 2 error. So type 2 error is when you didn't reject, but you should have. So let's take a look at what these types of errors will look like in an actual problem. The state of Georgia is considering spending $350 million on computerized mathematics curriculum for grades 3 through 10 that is intended to improve standardized test scores. They pilot the program with 250 students in grades 5 and 6 whose end-of-course test scores are compared to the state average of 150. So think about our null and alternative hypothesis here. You're trying to see if this program works. In the past, the average score was 150. We hope that the students are going to score better than that when they're using this program. So we would test these hypotheses. The null hypothesis is that the mean is 150, just like it's always been. In that case, the computer program doesn't make a difference. And if it makes no difference, then you don't want to spend $350 million on it. Okay, the alternative hypothesis that they're trying to prove is that the mean is greater than 150. So if the students that access this program score better than everybody else, you're going to think that it works and you're going to spend the money on it. So here we're saying the computer program works. Now, talk about errors. Type 1 error is when you reject the null hypothesis, but you shouldn't have. So if we reject the null hypothesis here, that means we're concluding that the mean is greater than 150. So type 1, we believe that the mean is greater than 150, but it's really not. So if you think the program works, you're going to spend $350 million on a program that does not actually improve scores. That would be pretty bad. That'd be pretty bad to spend that much money and then nobody's score actually improves. Now, the opposite of that, type 2 error. Type 2 error is where you fail to reject the null hypothesis, but you should have rejected it. So type 2, you fail to reject the null hypothesis, so you go along thinking that the mean is 150, you're thinking that the program does not make any difference whatsoever, so you're not going to spend the money on it, but really, you should have spent the money on it because student scores would have improved. So here's what this looks like. Type 2, we don't believe that the mean is greater than 150, but it actually is. Consequently, Georgia does not spend the money on the program, even though it would have benefited students. Now, if you're the state of Georgia and you're making the decision here, they probably will think that type 1 error is the worst case scenario for the state of Georgia because you spent so much money and it didn't actually work. If you want to avoid a type 1 error, you would want to pick a really, really small significance level, maybe 0.01, maybe you want to do 0.005, something really small to avoid making the possibility of making that type of mistake. Let's try one more scenario. Researchers are studying the effects of TV watching on cognitive development in toddlers. Recent surveys have shown that 21% of 3-year-olds watch more than 5 hours of TV per day, and reports from cognitive psychologists indicates that TV exposure may rewire the developing brain in adverse ways. They wish to test if toddlers who watch 5 or more hours of TV daily score less than an average of 40 on tests of cognitive ability when entering the first grade. Now, there's a lot of numbers here. We're trying to write a null and alternative hypothesis first. What we're measuring is the score. We want to know, do they score less than a 40 on this test of cognitive ability? So your null hypothesis is going to be that the mean is 40, but you're afraid that watching TV is going to make these kids score lower, so we're trying to prove that the mean is less than 40. So think about what that means as far as how much TV these kids are watching. If the mean is less than 40, that means their scores are lower. So here we can conclude that watching TV is bad. Watching TV is bad for the kids because it's going to lower their scores. But if the mean is 40, watching TV is okay. It's not going to harm their cognitive abilities. So watching TV is okay. Alright, so type 1 error. Type 1 error is when you reject the null hypothesis, but you shouldn't have because the null hypothesis was actually true. So if you reject the null hypothesis, that means you think that the mean is actually less than 40, but it's not. So if you think that watching TV is bad, then you're going to restrict children from watching a lot of TV when it wouldn't have actually impaired anything. So, what's the real consequence there? You don't let your kids watch TV, instead you make them go outside and play when they could have watched as much TV as they wanted and it wasn't going to hurt them in the long run. Okay, that's what type 1 would look like. All right, type 2. Type 2 is when you fail to reject the null hypothesis, but you should have rejected it because the alternative is actually true. So if you fail to reject the null hypothesis, you're going along here thinking that the mean is 40. You do not believe that the mean is less than 40, but it actually is. The consequence there, if you don't think that the mean is less than 40, maybe you let your children watch as much TV as they want without knowing that it will harm their cognitive development. Now, if you're the research company behind this, or if you're the parent, or if you're one of the children who one day grows up and reads this article, you're probably hoping that they avoid a type 2 error, right? Because type 1, I mean, what, you don't let them watch TV when they would have been just fine? Type 2 is the worst case scenario, in my opinion, here, because you're going to let them watch TV without thinking it's hurting them, when in the long run, it is going to cause some damage. So if you unknowingly cause your children damage, that's the situation you want to avoid here. Now, you can't control, you can control the probability of type 1 and have it influence type 2. So if you want to avoid type 2, you want to pick a larger type 1. Maybe you want to do a 10% significance level, because if you have a higher chance of type 1, that's going to minimize the chance of having a type 2 error.